Let's see, it's probably on the next day or the next one up. Let's see, here we are. What day is this going to be? Look, it's April 10th. It's the last cold front of the year coming through the Gulf Coast, and it's blowing out all the humidity. It's chilling the temperatures, but the sun, because of the seasons, is already at its kind of spring equinox level, and so the array is getting really good sunlight. It also has relatively cold surface temperature, and the production is at its all-time high at high noon, right in the middle of that perfect day without a cloud in the sky. The day that makes you want to go outside and ride your bike. That kind of crisp springtime day. And if I'm trying to capture every kilowatt hour that comes out of the system, as I would if it were a net metered system or a grid tied system, I would, if I could put it on a 8.5 kilowatt inverter, even though it's a 10 kilowatt system, and I still would capture every kilowatt hour that comes out of it at a 15% undersize. So in the industry, it's very common to undersize the inverter by 15%, no problem. And you can see examples of even greater undersizing, although this technique has diminished in importance as inverters have come down in price. Kind of on a final note about kind of this DC and AC relationship, where I see the most important item to know about right sizing is no longer the relationship between the solar array and the inverter that it's on. Again, mainly lower prices have reduced the importance of having the inverter be undersized. But it's more about sizing the system to provide backup power to the home with batteries, which is something that systems for the past 10 years without batteries have not done. And so for the last 10 years, we've had systems that kind of turn on in the morning and then produce a whole bunch of electricity and then turn off in the afternoon. So this might be a 10 kilowatt system, and this is a 3 kilowatt load. And so with net metering, 2/3 of the system production is bought back by the power company and then credited against the bill of, I guess I'm not going to draw that last circle there, but against the bill of the customer. And so the problem is our solar arrays are 10 kilowatts, and our average home load might be 2.5 kilowatts. And so you'd think the solar array would have plenty of power or capability to power the entire home. The problem with these kinds of smoothed out graphs is that if you increase the resolution on them, you would find that your home load actually jumps way up and down. And at some times your home load could be down at 500 watts, and then at other times your hot water heaters click on and your air conditioner clicks on and you go up to above 10 kilowatts. A tankless water heater by itself can be a 20 kilowatt load. Many air conditioner units have 10 kilowatt heating elements in them just to defrost the air conditioner. And so, our electric service panels, even though a home might be drawing 3 or 4 kilowatts on average, our electric service panels are designed for almost 50 kilowatts. And that's just a 200 amp service. And there's homes on 400 amp services that's designed for 100 kilowatts. Electric vehicle chargers are 50 kilowatts to 100 kilowatts. Just tremendous amount of power. And so I say that because now there's a question about the best way to join a battery to a solar array. And the question is, do we have the solar array wired directly to the battery bank through a charge controller, or alternately, do we have the solar array on its own inverter? And it's you the efficiency of the system, which is more energy efficient, is debatable, and the debate is a little bit nerdy because it's a very close together debate. You know, one system is not inordinately more inefficient than the other. The biggest difference that I can find between AC coupling and DC coupling is if the solar array is tied directly into the battery bank, then you only have one inverter for the entire system, and battery inverters do more and they're more expensive than solar inverters. And so your output of the funnel for the entire home is smaller, or at least more expensive. And what you can do with AC coupling is, instead of buying the charge controller that goes between the solar array and the battery bank, you're spending about the same amount of money on a dedicated inverter. And that dedicated inverter is going to add to the power output capacity of the battery system, at least during the day. And so, all else being equal, you know, an AC coupled system is going to give you more ability to power the whole house in the middle of the day with your entire system. And so that could be the difference between an off-grid system that doesn't run your air conditioning at all during an emergency versus an off-grid system that runs the air conditioner during the day during an emergency, and then turns it off at night to have the batteries and the inverter system serve other more critical needs. Although living in the South, I think the air conditioner is the most critical need. And so if you weren't following along on that tidbit, mainly is sometimes your solar array is going to be producing more power than your home, but if you zoom really far in on these graphs, the home load can be substantially greater than 10 kilowatts, you know, the size of a standard residential solar system. And so to have enough power to power the entire house when its load surges to its maximum level, it's nice to add the output capacity of the solar array along with the output capacity. I don't have any other colors. The output capacity of the battery inverter. You know, add these two together to handle those surges and peak loads, at least in the middle of the day, rather than go with charge controllers. So personally, I've moved over to AC coupling as even a off-grid design platform, because it just makes more cost-effective use of your budget, so that you can use the power from the array and the power from the battery and have a much larger end of the chute, so that you can use both of these output capacities at the same time to have the maximum amount of power possible going into the load, with a caveat that power could only be achieved in the middle of the day. So I have an off-grid system. The homeowners, you know, they love it. They love being off-grid, yada, yada. It's a regular house, but their only thing is they intended to have two washer and dryers so that they could do more laundry all at once. And that turned out that they couldn't have that, because when you added that to all their other loads, the system would be overloaded. If we had done AC coupling, they could have that high laundry load in the middle of the day swimming along just fine without exceeding the capabilities of their system. Okay, well, let's take a big step backwards and talk about inverter selection and pricing and how to break this down, because there's a couple other lessons to be learned here. So I just went online before class and pulled these prices directly off the internet. So these are, if I'm an installer, I might actually be able to get better pricing than what you see on the screen. But I think that but I wanted to reflect like retail pricing and pricing that you as a non-industry professional could just go online and find. And so here we have a 3,800 watt inverter, and it costs $1,350. And so if we take $1,350 and we divide by 3,800 watts, what we find is this inverter costs 35 cents per watt, and that's AC. Solar arrays are in DC wattage. So then you might take your total project budget and divide by your DC wattage and get a little bit lower price. But right now we're just going to stay in AC to compare one system to another. Now we go and we find this larger inverter. This is an 8 kilowatt inverter. So it's twice the size as the 4 kilowatt inverter, and it costs $2,035. So if we go and say $2,035, divided by 8,200 watts, this inverter costs 24 cents per watt. And so we've almost got a 33% pricing discount by doubling our project size from 4 kilowatts to 8 kilowatts. The price has gone down by 35%. That's a rather steep come down in price for two, as far as residential goes, fairly similarly sized components. And so this is why I say, like, nowadays, just erring on the side of oversizing the system is not as expensive as it used to be, and can sometimes be more worthwhile. I'm not saying overdo it, but I'm saying don't worry about this relationship as much. Now, since we're on this topic, we saw this Fronius inverter ranging from 24 cents AC to 35 cents per watt AC. What about this Solar Edge inverter? This is a 33 kilowatt inverter, and so that's even larger than the 8 kilowatt we just. I closed my calculator, ruining my vibe. We'll open it back up. All right, there we go. So we're going to take the $2,750 small commercial inverter price, and we're going to divide by 33,300 watts, and we get a price of 8 cents per watt. That's even that's tremendous. We got a 33% discount from going from here to here, and now we're getting an even more of a discount going down to this Solar Edge inverter. There's a difference, though, between analyzing, say, a Solar Edge inverter and a regular string inverter, because Solar Edge, they have to have these little individual boxes that get wired to each panel and then wired to the inverter itself, whereas a string inverter, it doesn't have the boxes, so it doesn't have as good a shade mitigation. It might not meet electric code for rooftop solar in the United States as rapid shutdown requirements, but on a ground mount on a utility scale system, this inverter is working just fine. There is a discount from going from 8 kilowatts to 33 kilowatts in terms of string inverter capacity. However, the Solar Edge inverter has less stuff in it than a traditional string inverter, because some of that stuff has been moved into these module level control boxes that are part of the platform. And so if we look at this 8 cent a watt range, and then we say, okay, well, we're going to have to buy one of these boxes, and regardless of the model, they're about the same price. when it comes down to it. And so now, let's say we bought a nice, 330 watt solar panel, and these boxes cost $72 each, according to this website. So $72 divided by a 330 watt solar panel, that's another 21 cents per watt. And so, and that's DC, and so it's going to be a little bit larger when we get to AC, and we did all of our other numbers in AC. But let's just give it the benefit of the doubt. We'll say 8 cents a watt plus 22 cents a watt. The total system, turns out to be 30 cents per watt. And so kind of comparing these systems together, we have 34 cents per watt for a small residential string inverter. This gets down to 26 cents per watt for a larger residential string inverter. It could go down even cheaper the larger the system gets. And we're also seeing the SolarEdge system coming in at, around 35 cents per watt. Just talking about kind of retail pricing that you can find online here. What about microinverters? So here we have two other things. Here's a SolarEdge string inverter at the residential level. So since the numbers are fresh on our mind, $1,700 divided by 7,600 watts, 22 cents per watt for the inverter itself. So by the time we add in the optimizer, we're looking at about 40 cents per watt for the inverter system. Here is a similarly sized inverter. They're both 7,600 watts, but this one is a battery inverter, whereas this one is not. And without doing the math, what we can see is the battery inverter is over twice as much as the batteryless inverter. So, battery inverters we see there are more expensive than just standard solar products. Here's the popular in-phase microinverter, and what we see is that for a 250 watt output capacity, let's say we put that on a 300 watt solar panel, and it's $111. And so if we do, normally I would take that and divide by the DC capacity of the panel, but what we're saying is $111 divided by the 240 watt continuous output of the microinverter, we're up at 46 cents per watt for the microinverter. And so what we saw is the SolarEdge system came in to be around 44 cents per watt, and that holds true when you competitively bid it out as well. The SolarEdge system is just slightly less expensive than the microinverter system. So a lot of solar installers prefer the DC optimizer platform because it saves them a little bit of money for relatively the same value set that you get with microinverters. Although if it's your first time doing solar, and that could be a do-it-yourself project or even a commercial project, and you want to use a crew that's really good at electrical work, like an electrician, electrical contractor, but they don't have any solar experience, spending more money to get microinverters can lower your labor costs potentially. So there's fans of all of these different types of products, and now we're breaking the price out kind of per watt. Let's do the same thing with solar panels. And so now we're going to be talking about kind of price per watts in terms of DC, and that's more of the industry standard. But here we have 30 solar panels, at 325 watts each. And so if I do 325 watts times 30 panels, that's almost 10 kilowatts for one pallet. Okay. So if we have $6,335 for the pallet, and we divide by almost 10 kilowatts, that turns out to be 65 cents per watt. Okay, so that's a Canadian Solar 325 watt module with some fancy features. Let's look at the price of a individual solar panel. If we don't buy the pallet, if we just buy the individual panels. So here's a $522 panel, and we're looking at 360 watts. That's a dollar, 45 per watt. Now, it's also more efficient. It's a 360 watt panel instead of a 325 watt panel. Both kind of standard brand names in the industry. But what we're seeing is the higher efficiency costs more money. We're also seeing that the just buying one panel instead of a whole pallet costs substantially more money. Here's a different panel that's 360 watts, and it has an even better all black look, and it comes from a well-respected brand, and its individual panel pricing is less. And so another lesson is, panels can have a pretty wide price range. It's good to design by the pallet. By the time you get into the industry, like this is pricing that I get from my one of my preferred vendors. I'm a smaller company. I buy a couple of pallets here and there, but not regularly, so I can't attract substantial pricing discounts on volume. What I do instead is just good old-fashioned supply chain management, and I also organize my project scope so that when I request pricing from a vendor, they treat me seriously. And anyway, what we see in these pricings is 46 cents a watt for a pallet of solar, or 47 cents a watt for solar that is slightly more efficient. And then this is a black on white module, and my preference is for black on black, because black on black is this. It looks better on a residential rooftop. So I'll pay a penny a watt more for that black on black aesthetic. Absolutely. No doubt in my mind that's a good deal. We're also seeing this higher wattage panel might be a 72 cell instead of a 60 cell. To kind of justify its lower pricing. So anyway, so now we're seeing solar module pricing. If you roll up your sleeves and do some supply chain management, you can buy modules for 45 to 50 cents per pallet. If you just go online and buy a pallet from a vendor, you're going to be paying 65 cents a watt. Okay, so another step in a good solar design is knowing the policy in your area so that you're compliant with your utility. And the United States does not regulate the price of electricity by each individual state. In fact, there's a court case going, I think, in front of the Supreme Court or being appealed up to the Supreme Court out of New Hampshire that is asking the federal government to step in and govern solar buyback rates between the utility and the consumer. It's actually a anti-solar group that is making the case. I think that backfire spectacularly on them because there's a lot of regions in the United States that have terrible solar policy that could easily be improved upon by the federal government. I don't think the case is going to get anywhere actually, because the United States federal government does not regulate the price of electricity, at the state level. And so that means to know your solar buyback rate, you need to know your state policy. And to know your state policy, you can go to this Desire database. And it's going to tell you all sorts of things. Back in the day, we used the Desire database to identify solar grant and rebate subsidy opportunities, and then design the systems around those opportunities. But let's say I'm doing solar work in Arkansas. I go to the Desire database, and I could go in and add, that's by sector. What I want is filter by technology. Let's do solar. So here's various policies for Arkansas as well as the U.S. government. You can find out information on the tax credit, for example. And here's Arkansas's net metering policy and interconnection guidelines. Let's see what we learned. So here we have Arkansas net metering, and it applies, this is important, it applies to both investor-owned utilities and electric cooperatives. Some states exempt the electric cooperatives from the net metering policy, but require the other power companies to do the net metering. In other states, not all the power companies may need to do net metering. It might be only the monopolies. Or in other states, they don't have net metering at all. And so from one state to the next, a solar array in Kansas City, Kansas can be very different from a solar array than in Kansas City, Missouri, just based off this net metering policy. And so what we see here is Arkansas's net metering policy, which recently got affirmed by their state court, said that to apply the system for net metering, residential customers can do no more than 25 kilowatts. Now, is that AC or is that DC? The technically correct, most appropriate way to talk about solar to the customer is talking about the DC capacity. Now, I guess that's the standard industry way. But in terms of your utility documents, the utility does not care about how large the gas reservoir is in a diesel generator. They care about the output capacity of the diesel generator. Similarly with solar, when they're talking about, the largest you can interconnect is 300 kilowatts or 25 kilowatts, the default is to be referring to the inverter output capacity. Now, sometimes solar, they step in and say, oh no, we meant AC or DC to kind of whittle down the allowable sizing. At any rate, it's already a made-up regulation. So, what this is telling us is in Arkansas, we don't want to do a residential array larger than 25 kilowatts because that would disqualify the system from net metering. On top of that, there's this saying 100% of the customer's highest monthly usage in the previous 12 months. And so that's another constraint about not oversizing the system. And actually, monthly energy usage can vary quite large from year to year. So it can, that can be another wrench. A lot of states, to overcome that, will allow you to do 125% rather than 100%. They might do on the annual usage rather than the monthly usage. All these little nuances you need to kind of identify when doing solar professionally so that you don't make a mistake and sell a system to a customer that's not as valuable as what you told them it would be. Commercial here, they're allowing larger systems. Of course, we talk about in other classes, commercial systems don't, unless they have to be on an energy only rate for net metering to make a lot of sense. And so it gives us, the nuances of net metering. This is a sizing class. What we're looking up is the size. You're trying to determine what's the easiest system to interconnect to the grid. We would check our net metering policy to make sure we're not oversizing the system, disqualifying us from net metering. If you have net metering, you want to go get it. And then we go not to the net metering section, but the interconnection guidelines section. And what this will tell us is the largest allowable system sizes. So Arkansas is also saying we're not going to allow you to interconnect a system larger than 25 kilowatts residentially and 300 kilowatts for non-residential. You might also get things like insurance requirements and external disconnect switches, although now the external disconnect switch has been added into NEC 2020. And so I guess what I wanted to just mention is there is a website that you should go to determine your interconnection guidelines and procedures. In some states, you'll find different insurance requirements based off system size. So over 10 kilowatts might require insurance or proof of insurance. Under 10 kilowatts might not. And that can craft your project development strategy. Certain levels may require higher reviews, engineering stamp. So here in the Desire, you can actually find contact information on who to follow up with to get more information, not just from your utility, but also from the state. Okay, so what we want to do is take a palette of solar and then say, okay, well, how do I pick out the right inverter for it? So let's say I understand buying a pallet of solar panels is going to be cheaper than buying them individually. So if I go buy a pallet of solar panels, how do I know that it's going to work with my inverter? And what are the sizing opportunities involved? Well, by and large, microinverters are worry-free. You could pull open this Canadian Solar panels spec sheet and find the in-phase sizing calculator on their website, and all you're doing is putting in the spec sheet information, the open circuit. Primarily, the open circuit voltage is more important, more of a design constraint than the operating voltage. The open circuit voltage, they're going to check to make sure you're not exceeding, electric code. On a string inverter, that might be 600 volts. On a microinverter, it's all AC, so it's more just, is the module voltage going to explode the internal circuitry of the microinverter or not? The good news is panel voltage falls into classes. And so if you have a traditional residential 60-cell panel, it's going to have a voltage that's similar to its peers, and it's going to be compatible with this inverter system at any rate. When you're doing the voltage checks for compatibility, remember that the inverter's voltage rating is under a laboratory standard test condition. And so in old school solar, we would look up on the spec sheet, grab its temperature coefficient, and go and find the record lows and record highs. Here, we're just plugging in the temperature coefficient, and Enphase is going to do a rough check. these temperature coefficients are general enough that in electric code you actually have a table that will, as long as you're using silicon panels, allow you to use the table to check your voltage range rather than the individual panel itself, because they're that close together. And then the short circuit current and your local temperature input. So this stuff is very common on all inverter sizing softwares asking you for the temperature range. And what they're doing is they're taking that and they're taking the module spec sheet and making sure that your maximum system voltage is within range of the electronics and within range of National Electric Code. But as far as the microinverters go, it's like one microinverter per solar panel. And so if you have a 60 cell residential solar panel, you use the 60 cell, microinverter, and it's compatible with pretty much any 60 cell module. One of the common, I just caught this mistake at the end of last year. A solar company sold some material to a customer using old solar panels and old microinverters, and their funky old solar panels turned out to be residential sized, but they were 72 cell panels, and they were putting them on 60 cell microinverters. So without even knowing the spec sheets or the actual specs, it's like, no, those aren't compatible, or probably not going to be compatible because they're not in the same kind of category. So what else can we glean from this spec sheet other than module compatibility? We don't really have to worry about the voltage range and amperage ranges of microinverters between the module and the product, because it's just 1-to-1. As long as it's 60 cell, it's all going to fall in line. The circuit design. So we have 30 solar panels. How many of those panels are going to fit on one pallet? Well, that's actually pretty easy. The microinverters are outputting 1 amp each, and Enphase forces their system onto 20 amp breakers. And electricians know that you can't just put 20 amps of output capacity on a 20 amp breaker, because then the breaker will trip. You have to do less than that. And NEC, the standard AC kind of oversize is 25%. And so you can only, on a 20 amp circuit, you can only have about 16 amps of output capacity. And what that means is on the Enphase microinverter that outputs 1 amp, you can only have 16 microinverters per 20 amp branch circuit. And so this is pretty easy. If I'm buying a pallet of solar panels and I see that it's 30 panels in a pallet, I know that's 16 per pallet. I can say, okay, that's 2 branch circuits. That's really easy. And so if I'm trying to optimize my project and I have a pallet of panels that's 24 panels or 25 panels, and I get another pallet that's 30, if I have good net metering and I still have the electric bill, 30 panels divides 15 per circuit, you can have up to 16, and that's great. If I have a roof surface that's as such where I can only fit 24 panels on my rooftop, then I might go buy a pallet based off the pallet quantity. If it has 25 panels per pallet versus 30 panels per pallet, sometimes that's the difference in kind of nailing your project in terms of hitting your budget needs. So microinverters are very easy to design with. You can have up to 16 per 20 amp branch circuit for their residential product. For commercial, it's let's see. Where were we? For commercial, it's actually a little bit fewer per branch circuit, namely because the inverter system is larger. So what we're going to do now is take a 10-minute break. And when we get back from break, we're going to look at sizing examples between the arrays and like a regular string inverter system, and kind of talk about what goes into determining how many panels can go on what circuit and what design flexibility there is in that. After that, we're going to take a look at battery sizing and see how you can start sketching out what size of a battery bank you would need for your home load and for your on-site solar. And then let's see, we're going to do a little bit of payback calculations and array layout discussion and budget discussion, and we'll call it a day. So think about questions that you have over the break. You know, it's about 5 after now. We're going to pick up at 15 after and then do another 45 minutes. So let's take a 10-minute break, and we'll pick back up at a quarter after. We're going to pick back up in about a minute or so. All right. So, welcome back. With the next step in completing your, say, solar design or solar interconnection application is to submit the interconnection application to the power company. And normally these documents can be found on the actual website of the power company itself. Sometimes, if you don't know where to go, sometimes you get them from the state. Sometimes you can find the contact information on the Desire website. If you can't find interconnection applications on the utility website, usually you can give their customer service department a call and then ask for the distributed generation department. But in terms of actually giving that distributed generation department the documents they need to approve your solar array, uh, we know that we can have up to 16 microinverters on a given circuit. And so as far as giving them a one-line diagram, it's pretty easy to do. Enphase has gone so far as to make a wiring diagram, which shows the actual individual wires. A single line diagram or a one line diagram simplifies this run and might have a little detail that says what wires are being denoted, but usually utilities are asking for an even more simple single line diagram. It used to be we would draw these out, in a drawing program, whether it be, I don't know, there's a CAD or something cheaper than that. Um, this one, it wouldn't be too hard to create your own here because Enphase limits their circuits to 20 amp breakers, and B, there's just up to 16 panels, and so you could just literally take this CAD file and change it to specify how many panels are along that circuit, and that you would have a wiring diagram for one circuit solar array that would be good enough for some jurisdictions. You could then go ask your electrician, hey, what size wire do I use on 20 amp wiring? And they'd probably get it correct because it's just AC. You can do Romex through the attic with microinverters. And if you're using string inverters or DC optimizers, the design is a little bit more complicated. Now, this kind of document I don't hand draw. I use computer software for this, and we have a design your solar roof class that focuses more on the design aspect. But what I can see from this document is this one line diagram is for two string inverters. I say there's string inverters because we just have, traditional circuits of solar panels being wired directly into the inverter box. and various disconnect switches and gingerbread and what that. With microinverters, the only difference between the one-line diagram for a string inverter and that for a microinverter is coming off of each solar panel, you're seeing the microinverter box referenced. Sometimes there will just be a little detail because some microinverters do DC optimizer does one optimizer for every two panels, and traditionally residential systems do 1-to-1. Of course, doing 1-to-2 is a little bit cheaper. And so the question becomes, well, how do you determine, in phase, the microinverters, they just told us, up to 16 per branch circuit. Okay. Microinverters are very flexible. If you just wanted to do a one-panel solar array, you use a microinverter and be just fine. String inverters, you have to know how many modules you can wire up in a circuit so that you don't overload the string inverter. And that has to do with those temperature coefficients that we were talking about earlier. There's software you can use, string sizing software that's manufacturer specific, where if you give them the inverter you're using and you give them the solar panels you're using, they will tell you how many modules can be on a circuit. It used to be that you had to have the same number of modules on each circuit and they both had to face the same direction. That's no longer the case. So when we do our example, we'll see that nowadays string inverters can have independently tracked inputs. Whereas to get that independent tracking in the past, you'd have to do module level controls. Although, as we've talked about in other classes, these module level control boxes are essentially mandated by National Electric Code on top of roofs. So almost every rooftop project in the United States now has these module level, whether they be microinverters or DC optimizers. And that's one reason that solar is more expensive in the United States when they talk about, red tape cost. The benefit is that these module level controls do provide additional safety. They just don't have them there for no reason. Okay, so in a regular string sizing software, you're inputting your temperature conditions and you're inputting, what inverter you're using. And so, if we go and buy 10 kilowatts worth, one pallet of solar, we would go and buy, we could select, this is a 25% undersized inverter. We could buy a 7.6 kilowatt inverter. We could also buy a 10 kilowatt inverter. Personally, nowadays, I wouldn't undersize by 25%. I'd just go spend a couple $100 more on the next size up. You're putting in your modules, and it's giving you the voltages and the amperages that are pulled off your specific solar panel's spec sheet. So these manufacturer string sizing softwares just have a database of like every solar panel out there, young and old. And then we get to a screen that will tell us, okay, my string inverter can have, 2 circuits on input 1 and 2 other circuits on input 2. These are called maximum power point tracking for the inverter itself. I think that's a distracting term. I would just call it, MPP1 is input 1 and MPP2 is input 2. And the difference is these two sides of the inverters can have, each side has to be uniform within itself, but not to each other. And so what we'll see when we do our example is we can, on side 1, we can have up to 2 circuits, and the links can be a minimum length of 3, a recommended minimum length of 7, and a maximum length of an 11. And what that's going to do is have the inverter operate in a good voltage range by not exceeding too much voltage, but also having enough voltage. But what does that mean? So what I'm doing now is pulling up an inverter spec sheet. Come on. So here's a inverter spec sheet. They're for different sizes. I actually like this residential one. And so what we see are these are small residential inverters. This one is a 3.8 kilowatt output. This one's a 5 kilowatt output. Okay, now they're saying the solar array could be oversized going into it. Okay, that makes a little more sense. What we're seeing here is it says, hey, there's a voltage range for these things where we have to have a minimum voltage of 200 volts and a maximum voltage. In this case, it's made for Europe and it's 800 volts because they have a 1,000 volt maximum. In the United States, we have a 600 volt maximum. And, that means we can have fewer modules on a circuit, and that means our systems have more circuits, and that means they're a little bit more expensive. So there is a maximum voltage range and a minimum voltage range, and the string sizing software makes sure that we're staying within that range to not undersize our array and also not make an error by oversizing the array. And these are pretty easy to use interfaces. So easy, in fact, it's worth just reviewing it one more time. We talk about this in the Design Your Solar Roof class, but we're here right now. So let's, just pull open an example. So this is, I'm not partial in any way, shape, or form to Fronius. I usually don't use Fronius because they don't have, rooftop panel electronics like DC optimizers or microinverters. If I was to use a Fronius inverter, I'd have to go buy a Tego DC optimizer for rapid shutdown compliance. But anyway, I'm going to pick out, we would probably, if we're looking on a 10 kilowatt array, we would either choose an 8 kilowatt inverter and say, okay, that's enough, or we might just say, who cares? I'm going to do 10 kilowatts. Let's do this 8 kilowatt. And we put in our temperature ranges. Just going to select a random, kind of the first brand name that I see of any repute. So, all right, I guess we'll always use Canadian Solar in our examples. I'm very module agnostic too. So we're going to pick out, 320 watt polysilicon panel. I just happen to know that 60 cell panels are around 40 operating volts. And so, I'm reasonably confident this is a 60 cell panel. If I went and I picked a 72 cell panel, the additional cells means it's going to have a higher voltage and we're not going to fit as many panels on a circuit, but that's okay. Anyway, we get to our input ranges, and remember, we're doing a 30 panel palette. And so we have to determine, of these 30 panels, how much are on circuit A and how much are on circuit B. And what we could do is, 2 strings of 20 and 1 string of 10. And that would be, right within, it's saying, okay, you're not, doing excessive oversizing, you're right on the edge, but that's fine. That's optimal. Or I could do 2 strings of 8, that's 16, and then I could do 2 strings of 7 for 14, but it's saying, this 2 strings of 7 might be a little bit undersized. It could benefit from a slightly altered, a slightly larger circuit to hit that minimum operating voltage. If I don't hit that minimum operating voltage, the field equivalent is that, the sun is turning the array on at 9:30 a.m. instead of 8:30 a.m. so the array just doesn't have enough voltage to turn on. And if you really got into the advanced details, that scenario would occur on hot days when performance is dragging down the array in the morning or in the evening, the array just turning off because of temperature degradation of voltage more than anything else. And so we can use the string sizing softwares to stay within the voltage range and the amperage range of the system. Let's get back to our presentation here. Where was I? Just give me 1 second. I'm not seeing. I got too much stuff open. I minimize it. I don't know. I'm just going to open it back up. Well, sorry about that. I think I closed the presentation. Well, anyway, we are going to be back on track in just a minute. If now's a good time to type in questions, and I'll get to them as we kind of close out the rest of class. We're about to get into battery bank general sizing. Kind of so what we're seeing in the string sizing software are circuits of about 7 to about 11 solar panels. And if we moved over to higher voltage panels, we might see 6 to 8 solar panels. If we when we add DC optimizers into the mix, to fully appreciate the DC optimizer sizing, we have to understand how the DC optimizers work. And we're going to kind of close on that topic at the tail end of the program, because we're going to talk about kind of finalizing your designs and what are some advantages of DC other design advantages technically, from a technical perspective, that module level voltage optimization gives you. But as far as the sizing software goes, it's the same as string inverters. You're entering the panel you're using. You're putting in how many solar panels you're using. You're putting in the array tilt and orientation and location. And then it just spits out, okay, well, you're going to use these, this 10 kilowatt inverter, and each inverter is going to have 3 circuits, and that'll be 6 circuits total. And it's recommending what optimizer to use. And so basically, your manufacturer design tools will tell you the ultimate, like, how many modules are going to go on a circuit, how many what optimizers are compatible with your solar panels, what microinverters are compatible with your solar panels. And so let's take a step back and look at our budget. Let's say we bought a pallet of solar panels for 44 cents per watt. And we do some pricing on our Solar Edge system and competitively price it out. We get that down from 40 cents a watt down to about 33 cents per watt. Racking is about 15 cents. I always recommend a healthy balance of system material budget, because even if there's no upgrades that need to be done on an electric service panel with solar, I find that spending a little bit more money on your balance of system material can help you achieve better installation quality. And particularly with solar labor, if you can enable general electrical contractors to do the install, general roofing contractors to do the install, that can lower your labor budget as well, without necessarily sacrificing your quality. Because you can't tell me that a roofer doesn't know how to do good roofing, or an electrician doesn't know how to do good electrical work. That's their jobs. The problem with getting those contractors out to do solar is they don't have enough instruction. That's on the designer and the manager to say, well, if we want to just pay our labor for the work that they do on site and not for additional overhead affiliated with a turnkey contract, to get a good labor budget with good trained workers, it doesn't need to cost an arm and a leg. A turnkey contractor might charge over $1 a watt for the project just because that's the business that they're in. As engineers, you might be more capable of managing the project on your own. This is typically around what I budget. Paying good workers, qualified licensed workers for, by just saying, hey, show up. Here's the permit document. If you need any help, I'll tell you what to do. Then we get into profit and overhead that the turnkey contractor might add onto the top of the project, and any sales taxes. So I think $250 a watt is an achievable project budget when we're talking about pallet-sized projects or slightly larger to achieve. Typical industry pricing is around $3 a watt, to give you kind of an idea of the range of a turnkey markup. So as a developer, as someone who's interested in solar, not someone's doing solar, you might take a step back and say, well, what budget do I need to really get a good payback on the system? You don't want to take the word of the sales rep selling it to you. You want to be able to calculate your economic model on your own. What I would say is, here we have our $250 per watt budget, and a number that I think is very useful to know is how many dollars per watt a solar array saves you per year. That's a number that a lot of installers don't know. They'll what it is if you know how many kilowatt hours a solar array will produce, and you know the dollars per kilowatt hour, you can multiply those numbers together to get a dollars per watt. And so we can use PV watts to say, okay, I'm doing a 1 kilowatt. In our example, we did 10 kilowatts, but I'm doing a 1 kilowatt array, and that's producing 1,000. In my case, it was 1,500. Well, let's just say it's 1,400 kilowatt hours per year. That means 1 watt produces 1.4 kilowatt hours per year. Okay. Well, if I know that 1 kilowatt hour is worth 10 cents a kilowatt hour, let's say I'm net metering and the utility's billing me 10 cents and they're crediting me 10 cents, and the value of that solar electricity is 10 cents per kilowatt hour, and I know that 1 watt produces 1.4 kilowatt hours a year. I multiply those numbers together, and what I get is 14 cents per watt per year. And so at 14 cents per watt per year, how many years do I need to get up to $250 a watt? There's a lot. If I want a 10-year payback on my project, and I know my solar array is generating in my area because I know my generation rate and I know my solar production figure, 14 cents per watt per year, then for a 10-year payback, I need a budget of $1.40 per watt. And so, the federal tax credit is actually stepped down. It's now 26%. And so really what to update this slide to get a 10-year payback at 10 cents a kilowatt hour with typical solar production figures, I need a budget of $1.90 a watt in order to get a 10-year payback. Now, if the market said the solar value was 15 cents a kilowatt hour, then the payback might be 6 years. or I could accommodate a higher installation budget and still get a 10-year payback. But I think it's useful to know what your dollar per watt per year payback number is. You get that by multiplying the production of the array with the effective value of your electricity. But I just think for most of the country, even with good net metering payback, outside of California, outside of New York, but in the middle of the country, average electricity pricing, average sunlight, you're going to need a project budget of $2 per watt or less to get that 10-year payback. And so I think it's important to start thinking creatively about solar design and not sizing the system to do 100% of the electric bill and being reliant on net metering, but to look for other opportunities of sizing to say, well, the last 10 years we've had net metering and it's been a crutch that's enabled solar to come to market for consumers, which I think is a good thing. I think it's good that the utility has competition directly with their customers, particularly on monopoly grids. But let's be real, the reason that net metering has been necessary is because all of the solar electricity during the day has been dumped onto the electric grid. And that just, if we want solar to be 100% of the grid down the road, we have to be a little bit more advanced than just assuming that all of the electricity from the grid can be sold. So a different approach is to undersize the solar array and use that project budget for a battery and maybe look for rate structures that have a peak versus an off-peak rate, where maybe a sliver of the facility is at a very high peak rate, and then every other time outside of that is off peak. And so if you can design a solar array and a battery to eliminate the peak rate, and then you avoid the high cost of the peak rate and you save money because the rest of the energy use is now being billed at the off peak rate. And so variable peak rates and batteries and solar are now pushing that payback discussion further to say, actually, for most of the country, it's really hard to get solar down to a payback that is under 15 years. And if you do, you're in a market where there's subsidies for solar, and that can result in a deal that is almost too good to be true sometimes. And the short of it is that those opportunities are short-lived. So if you do have local incentives and local subsidies, it's probably in your best interest to go out and get them, even if politically you believe it might not be in society's best interest to have them in the first place. The opportunity for you with that subsidy that brings solar down to a 5-year payback or 6-year payback is short-lived. I had a customer who bought a $75,000 solar array, and the utility wrote him a $50,000 check. And then he got a $22,000 tax credit. So this $75,000 system, it only cost him $3,000. Wow. Okay, well, I only sold one of those because then the rebate program crashed and they canceled it. They called it a victim of its own success. So anyway, we have to be a little bit smarter about solar and battery design. So I think we're going to end on array layouts, but I think it's a good time for us just to do a simple battery model in PV watts to kind of figure out the right size between a solar array and I guess what we would start with is determine the size of a battery bank to power the whole house off grid. And then from that point, you can take a step backward and start building out a truly developed model that might involve a generator and other things. We need to take that baby step to say, okay, here we have our PV watts model. And what we know is our system output in watts. And to make things a little bit more clear, remember we just went to the PV Watts website and did an energy model, and this is, up until this one modification, this is what you get directly from PV Watts. So we're going to turn this wattage column into a kilowattage column by dividing by 1,000, and that's going to make things nice and neat in kilowatts. And to make the sheet a little bit easier to read, we're going to hide some of this project data and just focus on system output. We'll hide the watts too. Okay, so the next thing that we need to put in is our consumption. And we might not know our hourly consumption of our building, and we also might have to make some assumptions. So what we're going to do is we're going to say, okay, there's 12 months in a year, right? And a lot of customers can have a lot of customers will have a record of their 12-month electric history. Even if they only have one electric bill, it'll often reveal just as a bar graph the 12-month electric history. And then the Energy Information Agency will tell you typical household energy consumption numbers for your area. Now, down south, it's 14,000 kilowatt hours per year. However, solar customers generally use more electricity because they live in larger homes, more people inside that house. They're above average homes at the very least, to say it modestly. So we're going to take that 14,000 number and elevate it up a little bit in terms of developing an assumption. And so what this is going to be is a lot of months, or at least the lesser performing months, are going to have 1,000 kilowatt hours out of 1,700, and this is, we can fine tune this with actual customer data. But then maybe the summertime months are going to be at higher than that, and the winter months are going to have high electric use as well. So what we're doing is saying you can take, if you have the month by month figures, if these were actual real numbers and month by month electric bills, then you could take the days of the month. Maybe I should have made this before class. But you can divide by the days in the month, and then you can divide by the hours in the day to get an hourly electric load. So in January, my house is averaging 2.7 kilowatt hours of electric load, and then in August, the house is averaging 3.3 kilowatt hours of electric load. Now, in reality, that load could be 40 kilowatts for 1 minute, and then drop down to 8 kilowatts for 5 minutes, and then down to 500 watts for 10 minutes, and then back up to 10 kilowatts for 10 minutes. It's chaotic, but it would average out to be 3 or 4 kilowatts sustained per hour. So anyway, I would take these numbers, and we're going to assume now that we're going to add a load column, and because we don't have any more granular data than this, I'm just going to say, okay, well, for the entire month of January, my house is averaging 2.6 kilowatt hours of load for every single hour of the day and every single day of the year, or every single day in the month of January. And so I would for every single hour of the entire month. All right, we made it. I would say our house used 2.6 kilowatts of load. And then I would customize that for every single hour of the year. We don't have time to build that out in the last few minutes of class, and so I'm just going to say, okay, at 17,000 kilowatt hours, 365 days, 24 hours a day, that's about a 2 kilowatt hour load, and I'm going to assume my model is going to be a little bit off. I'm just going to. Does it matter that my model is off terribly? Well, it depends what direction you're going. What I would say is my winter loads are still going to be high. Really, this is going to overestimate my loads in the springtime and underestimate them in summer and winter. And so if I'm overestimating my load in springtime and underestimating my load in summer and winter, then what does that mean to my design? That might mean that I don't know. Let's find out. So we have our solar output and our consumption, and then the next step is basically you have to guess. You have to say, okay, I'm gonna start with saying my battery bank is 120 kilowatt hours. Well, let's actually start with 0. Let's assume there's nothing in the tank, and so I have 0 kilowatt hours, and then I'm adding my solar load and I'm subtracting my actual consumption, and then we just add it up for the entire year. So the hours are clicking by, and I'm drawing power out of the battery bank. And then the sun comes up. And, well, actually, because this is a 1 kilowatt array, it's or I guess a 10 kilowatt array, but this is just a particularly cloudy day. It's not really doing us anything. What is this array size? We need to go DC system size, 10 kilowatts. Okay. All right. So it's a 10 kilowatt system. The next step that I would do on my model is say, well, we need to make it for, a toggle here. And this is for a 10 kilowatt system. So we're going to divide by 10 to get a scalar, and then we're going to multiply it by our actual system size. And what that will do, then we have to go and update our column here to make sure we're using the right one. And so now we can change our system size, and it'll change around our model. 120 kilowatt array instead of a 10 kilowatt array. Let's go ahead and do, well, okay, I know a pallet is 10 kilowatts of panels, and so if I do a 2 pallet system, that's a 20 kilowatt array. And so now we're starting out with a 0 kilowatt hour battery bank, and I'm drawing power out of it at night at even 2.6 kilowatt hours. And then let's speed this process up a little bit. As the sun's coming back up, what we're seeing is the battery bank starts to fill back up, and then the sun goes down and the battery bank gets more negative, and the sun comes back up, and at any rate, let's make these numbers make a little bit more sense here. I'll say I'm going to do what I could do is just continue this exercise all the way down to the very end of the year. And my numbers start to get out of control. And that's because I've not just assumed, my battery bank has no real starting size. I've also assumed that it has kind of a unlimited size. So what I'm going to look at is the minimum size in this group. Hold on here. I don't know where that's generating a circular reference here, but the short of it is you have to go and then modify your Excel to say, if insert an if statement to say, okay, well, if the battery bank gets any larger than our starting size, which is going to be 120 kilowatt hours, take some energy out of that. And this is where I'm getting off right here. Needs to be equals that plus that. Oh. And so what we can see in our battery bank is we're assuming a starting size of 120 kilowatt hours, and we're drawing out of it. And in the wintertime, it keeps going down and it keeps going down. And now we're on like our third day and we're not producing as much power as we need. And then we're getting into, even though we've started at a negative battery bank, now we're down into almost the very bottom of our battery. And then the sun comes back up and we surge back up to 70 kilowatt hours and we start draining again. And remember, our maximum in this case is 120 kilowatt hours, and we're going fine. We haven't hit zero yet. We haven't gotten over 120 kilowatt hours yet. And all of a sudden we hit a sunny patch. We have to go make sure that the battery doesn't fill up above 120 kilowatt hours. And so, what we can do is just force it back down, and say, okay, on this day, the battery is now completely full until the sun sets, and then it starts draining back down again. And, there's only a few streaks of days where we're going to fill back up, but cumulatively, we do have to model that clipping or else it'll catch back up on you. I guess we didn't have time to fully build out the model in class, but I just wanted to give you kind of how you can start sizing a battery bank based off the PV watts calculation. What I then do for this is, in addition to restricting the maximum size of the battery bank, so that assuming that energy is lost, then I'll go and add an additional column for generator runtime. And essentially, when the battery bank gets too low or too close to zero, that's when I model or simulate, the generator turning on and charging the battery back up. And so in a class dedicated to off-grid, we would go further into this kind of model. What I want to end class today on is kind of optimizing the array layout. And so at its very basic level, solar is how many rectangles can you fit onto your usable surface area. And there are fire code and electrical code setback requirements, 3 feet off the sides, 3 feet off the top. The next thing to reduce your project cost is to make the project as easy to install as possible. And so what that means is, if we see that microinverter circuits can only accept 16 modules, you might look at your array layout and say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 17, 18, 19, 20, 21, 22. So this array is 22 modules long, and you get into circuit design. So it says, okay, do I start a circuit here and go 2, 4, 6, 8, 10, 12, 13? What I might do is say, okay, well, if does it make sense just to have the circuits all start and stop kind of in similar places? Where or does it make sense to kind of piggyback them and have the starting and stopping points look odd and random? And so where this really gets into is okay, you do want to fill up the usable surface that you have with a nice large project, assuming you're not running out of a net metered electric bill or overloading your battery or staying with other constraints. But when it comes to sections of an array, like this section of the array, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Well, it turns out that when we used this microinverter, you could fit up to 19 on a circuit. They had a lower amperage than the latest and greatest model. And so when we said, okay, well, we're going to fill up our south side, but we're also going to have a subarray facing east and a subarray facing west, intentionally designing that circuit so that it only has one circuit in that section and not two. Here's a home design where we had a large section on this portion of the roof, and then a small section on that roof, and a small section on the other side of that roof. And we isolated and intentionally isolated the circuits so that this circuit can fit that many modules, and then the other two roof surfaces, this side of the roof and the other side of the roof, share the same circuit. And so intentionally dividing up your circuits so that they fall into the subarray sections in a logical and easy to install order makes a lot of sense. Now, this brings us back to kind of our final kind of note. I thought I had put this slide into the program. Well, I guess not. Let's look at a SolarEdge power optimizer spec sheet, and I think it's appropriate that we bring this up in class because it's like the most popular residential solar system in the United States. And what we get on their spec sheet are the power outputs of the optimizers, the input voltages of the optimizers, and we can see that the 72 cell optimizers have higher input voltages than the 60 cell only optimizers, and that's why if you plugged a 72 cell module into a 60 cell optimizer, its voltage would be too high for its electronics and it would pop, and that means it won't work anymore. Coming down the spec sheet, we get into the information that would come up on the string sizing software, which is the minimum string length and the maximum string length. So remember, the minimum string length is giving the inverter a minimum of power so that it turns on. The maximum string length is giving it the maximum amount of power so that you're not exceeding the capabilities of the circuit. And what is special about DC optimizers is that a volt, let me make this a little thicker, a volt times an amp is a watt. And by doing voltage level correction at the panel itself, what the optimizer is doing is decreasing uh, the is doing one of two things. By toggling the voltage up and down, you have an inverse relationship where you're toggling the amperage up and down. And so earlier we said, solar arrays are designed around 600 volts, but maybe they're only operating, during their maximum power because of temperature degradation. Maybe they're only operating at 400 volts. What the Solar Edge platform does is by controlling the voltage of every single panel on that circuit, they can say, okay, but we're going to go ahead and step up the voltage. You're normally operating at 400 volts, and so we're going to correct that and increase the output voltage of the circuit, and that's going to decrease the amperage of the circuit. And because we're decreasing the amperage of the circuit along that 20 amp or 30 amp circuit, we can fit more panels. And so in regular string inverter sizing, those examples we saw earlier today, we got up to a maximum of 11 panels per circuit. And then with the in-phase microinverter platform, where we were restricted by the components, in-phase says we're going to build around 1 amp per optimizer and 20 amp branch circuits, and that's all you got. That resulted in 16 panels per circuit. But what the Solar Edge system, by staying within its DC architecture and using all the way up to the fully allowed 600 volt spectrum of United States electric code, and by actively controlling that voltage so that you can get the voltage all the way up to its maximum and the operating amperage all the way down to its minimum, instead of fitting 7 to 11 modules per string per circuit, they can fit 25 modules per circuit. And so that means when we're talking about optimizing the installation, here we have a subarray section that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 modules. If this were on a string inverter, 17 modules, we would have to have 2 different power points, and we'd have to have exactly, 7 modules and 10 modules, or 8 modules and 9 modules. That's probably how it would turn out. But we would have to have 2 circuits, and that would mean 2 wire runs and on this section down to the inverter. With an in-phase microinverter system, we could only have 16 modules per circuit. So we'd have to have 2 AC branch circuits up to this individual section. With Solar Edge doing voltage optimization within the array itself, by stepping up that voltage and decreasing the amperage, we can fit more modules onto the same circuit. And so that means you only need to have 1 circuit from the home up to the rooftop. And in other classes, I talk about how I use a pre-bundled cable. It's a flexible metal cable that comes with the wires already inside it. And so, I mount the inverter on the wall, and I might peel back some of the cable and stub up an EMT. But from that point, I'm already in a metal-clad cable all the way up to the point. I just run 1 circuit of this cable up to the rooftop, and the install's done. That's how you get into installation crews that can knock out an entire solar project in the course of a day, is by, fine tuning, minimizing your circuit runs, and material selection has a lot to do with that. And so if I'm looking at an array surface and there's only 16 modules or less on a job site, I'm looking at, hey, that's where I'm going to go with micro inverters, because it's just going to be quick and easy. If I'm looking at a surface and there's anything that's more than 11 panels and less than 25 panels, I'm thinking, okay, I have to do DC optimizers on that. And that's how your kind of material selection impacts your design. Uh, by and large, you can't go wrong starting with DC optimizers or starting with in-phase microinverters when you're on a roof. Beyond the voltage correction and the fire safety, things like a passing shadow on the roof surface, with these module level controls. That's no longer a design issue, whereas without those controls, it would be. So, okay, I hope we've learned more about sizing examples. If you were in class yesterday and you sent me an email for those slides from yesterday, I still haven't sent them out yet, but I will. If this is your first time attending the program, I've placed my email address in the chat. It didn't send me a message for questions. So we do have a question from Richard. It's an offline question. So Richard, you can just send me an email and I can answer it for you. And with that, I'm out of time. So here's my email address. I'm going to pass it back to Jerry, and y'all have a good rest of the day.
Great. Thank you, John. Very interesting, great discussion and presentation. Thank you. So for our participants, this is a 2-hour live webinar, and to complete the course, what you need to do is log into your student account and complete the survey. And we do read the survey responses, so if you wouldn't mind, give a little thought to it. We appreciate your feedback, and we do take it very seriously, and appreciate all the thoughtful answers we've been getting. And once you complete the survey, your certificate of completion for this course will be available, download and printing. And that concludes the webinar for today. Thank you for your participation. We appreciate it very much. For those of you who audited today's webinar, we'll send you an email as a follow-up for your feedback, and also explaining how you can obtain a certificate of completion if that's of interest to you. So thank you to everyone. Have a good day.
You too.